Hello everyone, welcome back to Two Maths. In this video we'll be going over functional equations. And before we talk about functional equations, let's talk a little bit about functions and some definitions related to functions. So a function, we all know, maps elements of the set A, which is its domain, to elements of the set B, which is its codomain. So a function is injective or one-to-one if we have f of x equals f of y if and only if x equals y. So what that means is if we have two sets, let's say set A and set B, with the following elements, if a function is injective, that means each element of B can only be mapped by at most one element of A. But this doesn't necessarily mean that all elements of B are mapped, because as you can see, some elements of B can be left out. So next we have surjective functions, which are also called onto functions. If a function is surjective, if for all elements B in the set big B, there is some A, at least one, in the set big A, such that f of A equals B. So this means that each element of the set B needs to be mapped by some element in the set A, and that is the only restriction. More than two elements of the set A can map to the same element of B, as long as all elements of B are mapped to. So visually this would look something like this. So as long as each element of B is being mapped to, then we can call the function surjective. And lastly, we have what we call bijective functions. And we define a function to be bijective if it is both injective and surjective. So visually that means if we have two sets A and B, then each element of B is going to be mapped to by some element of A, and no more than one element of A can map to the same element of B. Okay, so let's take a look at some problems involving functional equations. A functional equation is simply an equation that involves functions, like this one in this problem. So we have if f of x minus y equals f of x times f of y for all x and y, and f of x never equals 0, then we need to find all possible values of f of 1997. So often what we want to do, given a functional equation like this, is to eliminate one variable and find more about the function that way. And we can do this because the function is valid for all x and y. So we can just let x or y be whatever we want. So if we let x equal y now, to eliminate the variable y, then we have f of 0 equal f of x squared. So let's once again take advantage of the given that it's valid for all x and y, and we can let x equal 0 now to get f of 0 equals f of 0 squared. So this tells us that f of 0 times f of 0 minus 1 equals 0. Here we've just moved the f of 0 to the right and factored it out. So this tells us that either f of 0 equals 0 or f of 0 equals 1. But we know that f of 0 can't equal 0 because that was part of the problem statement. So now we know that f of 0 equals 1. But since we had that f of 0 equals f of x squared, we have f of x squared equals 1. So this tells us that either f of x equals 1 or f of x equals negative 1 for all x. So now let's find a little bit more about the function by eliminating x this time. So let's let x equal 2y. And if we do this, the function becomes f of y equals f of 2y times f of y. And now since the function never equals 0, we can divide both sides by f of y. And we end up with f of 2y equals 1. Since this holds for all values of y, we have f of 1997 equals 1. So this agrees with our earlier finding that f of x equals either 1 or negative 1. Alright, so what we just looked at was an example of how to find a specific value when we're given a functional equation. But many times we want to find a specific function, like f of x, when we're given a functional equation like this one. So we have f of x is defined for all positive integers, and we have f of x plus y equals f of x times f of y minus f of xy plus 1. So we're given that f of 1 equals 2, and we want to find f of x. So since we're trying to find f of x, our best bet would be to eliminate y from this functional equation. So since it's defined for all positive integers, let's define y equals 1. So if we do this, our functional equation becomes f of x plus 1 equals f of x times f of 1 minus f of x plus 1. So since we know that f of 1 equals 2, we can rewrite this as 2f of x minus f of x plus 1, which becomes f of x plus 1. So what we end up with is f of x plus 1 equals f of x plus 1. So since we know f of 1 equals 2, we know that f of 2 equals f of x plus 1, so that's f of 1 plus 1, which is 3. F of 3 then will become 4, and you can see that this pattern will continue, so that we have f of x equals x plus 1 in general. So we just used a pretty much straightforward inductive argument, but let's actually check that this solution works for the functional equation that we have. So here's the equation again. So if we have f of x equals x plus 1, that means that f of x plus y would be x plus y plus 1 equals, now f of x times f of y would be x plus 1 times y plus 1 minus f of xy would be xy plus 1, and we have the plus 1 term here. So on the right hand side we have xy plus x plus y plus 1 minus xy plus 1 plus 1. So this xy cancels with this xy, plus 1 cancels with negative 1, and we're left with x plus y plus 1. So we can see that f of x equals x plus 1 is indeed a valid solution. So the function f of x equals x plus 1 works for this functional equation. Okay, let's take a look at another example that involves substitution. So we need to find all functions f from R to R. So basically the domain is all real numbers, and the codomain is also all real numbers, such that 1 plus f of x plus y equals 2f of x times f of y. So since we are going from the real numbers to the real numbers, we can let y equals 0 to eliminate this variable in our functional equation. And then what we end up with is 1 plus f of x equals 2f of x times f of 0. So we can solve for f of x now. So let's take f of x to the right hand side. We have 2f of x times f of 0 minus f of x equals 1. Factoring out f of x, we have f of x times 2f of 0 minus 1 equals 1. So we have f of x equals 1 over 2f of 0 minus 1. So since 2f of 0 minus 1 is simply a constant value, our function f of x is going to output some constant. So let's call that constant c. So our function is going to be of the form f of x equals c. And we want to find what the possible values of c are. So if we let f of x equals c in our original function over here, we get 1 plus c equals 2c times c. Because recall that f of x for all x equals c. So both f of x and f of y evaluate to the same constant. So we get 1 plus c equals 2c squared. And now we can solve this quadratic, so we get 2c squared minus c minus 1 equals 0. And we can factor this now as 2c plus 1 times c minus 1 equals 0. So we either have c equals negative 1/2 or c equals 1 as the two possible solutions for f of x. So our original problem asked us to find all functions that satisfied that given functional equation, and our two functions turn out to be f of x equals negative 1/2 and f of x equals 1. And we're done. Alright, so now let's take a look at one final type of problem which involves the separation of variables. So here we have the domain 0, infinity, and we want to find all such functions such that y times 2 to the f of x equals x times 2 to the f of y. So the first thing that we can do is, because it's raised to the sum power of 2, we can take both functions log 2. So we get log 2 of y times 2 to the f of x equals log 2 of x times 2 to the f of y. And now we apply the identity that log base a of bc equals log base a of b plus log base a of c. So our equation now becomes log 2 of y plus log base 2 of 2 to the f of x equals log base 2 of x plus log base 2 of 2 to the f of y. So we can simplify this a little bit. We have log base 2 of y plus log base 2 of 2 to the f of x simply becomes f of x equals log base 2 of x plus log base 2 of f of 2 to the power of f of y simply becomes f of y. So the separation part comes where we separate the variables on two different sides of the equation. So we have f of x minus log 2 of x equals f of y minus log 2 of y. So what this tells us is that since f of x minus log base 2 of x equals f of y minus log base 2 of y, and this must work for all x and y in the given domain, then essentially this expression must be a constant, because no matter what we change the value of y to be, is going to equal this expression in x. So we have that f of x minus log base 2 of x equals c for some constant. So we find that f of x equals log base 2 of x plus c. And that is our general solution for this functional equation. And now what we can do is we can check the solution. So we have, since we have f of x equals log base 2 of x plus c, then y times 2 to the power of f of x becomes y times 2 to the power of log base 2 of x plus c. It becomes xy times 2 to the power of c. And now we check that this equals the left-hand side, so x times 2 to the power of f of y. This equals x times 2 to the power of log base 2 of y plus c. So we end up with xy times 2 to the power of c. So these two are equivalent. This means that our functional equation f of x equals log base 2 of x plus c holds, is a valid solution. So we're done with this problem. Alright, that was it for this video. Thank you for watching. If you have any more video suggestions, let us know in the Google form in the description, and see you later.